Okay, so in this one we're going to cover trees and graphs and like just terminology and stuff you can do with them. So we're going to start with tree terminology. So just to lay some base information. So we've got trees, and these consist of nodes, which are in some cases are called vertices. And connecting those are links, which are also called edges. So we can say in here, A, B, and C are vertices, and 1, 2, and 3 are edges. Well, actually, it should be like this. But yeah, you get what I mean. So we've got always in a tree there is a node, an origin node. So we've got, say, if we make a tree R, A, C, let's just say B for the sake of this, we could say that R is the origin node, and all trees have an origin. And in this tree we can see that we have some subnodes. So C is a subnode of R, and B is a subnode of A, and obviously A is a subnode of R. And so we can say that when a node has a subnode of its own, it's called a parent. So A is parent of B, and we can say that when a subnode has a parent, it's a child. So we could say B is child of A, and it's like reversible. So you can change in child for parent and switch up the order. Okay, so we also have something called a degree of a node. So a degree of a node, this is the number of children a node has. So we can say in this example up here, R has degree 2, A has degree 1, and C and B has degree 0. Because obviously R has 2 children, A has 1 child, and B and C have no edges coming off them, so they have no children.
Elliot, were you writing that? Because I think it might not be coming through.
Oh, it's coming. It should be below.
Yes, it's not there. Give it a second. Hopefully, she'll reconnect. As a test, left of the graph you drew of the RIB, drew a line. Can you see that?
Yep.
Oh, it's come through. There we go.
Yeah, I think it was me.
Yep,
as you can see, there we are. So I'll just quickly go over that again while that's on your screen. So degree of a node, R has degree 2 because it has 2 edges coming off it. A has degree 1 because it has 1 edge, namely B, coming off it. And then B and C have no edges coming off it, so they have degree 0. The degree of a tree is the maximum node degree. So what we could say for this tree, well, the maximum node degree we know is going to be the largest value, which is 2, So the degree of this tree is 2. We can say that a node without any children can be called a leaf. So we can say that nodes that are the root of leaves are called internal nodes. So what this means are, so let me write that out. So nodes that are not the root or leaves are internal nodes. Let me just rewrite our example so it's up on our screen here. So it's R, A, C, B. I think that's how I had it. So we can say that in this case, A is the only internal node in this tree, as it's not a root, which is R. So using R for root. And C and B are leaves. So then this means that because this is in the middle of 2 nodes, we can call it an internal node. And so trees are recursive structures, so any parent node can be seen as the root of a new tree. So what we can say is, well, we have this tree above, R, A, B, C. We can say that another tree that can be made is just AB. It's just a subtree of what our other tree is. This is also classed as a tree, with A being the root node and B being a leaf. Okay. So we're going to quickly have some rules as well that these have to satisfy in order for it to be a valid tree. So we must say that trees only have one path to each node. So essentially there's no 2 ways to get to one node. So we can see in our example, again, we'll just rewrite it out so it's on the screen. The only way you can get to B is by going through A first. If I had it like this, actually if I do that in a different color, if I had it like this, then this would not be a valid tree, as that would mean that there is 1, a cycle, which we'll get to in a bit, and 2, there's 2 roots to B. And that means there's also 2 roots to R. Well, R being the root, that's a different case. But you can see there's 2 roots to C, because you could go R, A, B, C instead of just R, C like it should be. So in order for it to be a tree, trees only have 1 path to every node, with all paths starting at root. Similarly, we could say then, if all paths are starting at the root, then all nodes must have a path to the root. Because if they all start at the root, then they must all have 1 to the root, because you can just go backwards. What we can have is another. So we've been basically just looking at binary trees for now in these examples. There is one other case. We can have a family tree. There's something called a family tree. So a family tree, one thing it can have, it allows for you to have 2 parents to a node. So if we literally think of this like a family tree, like a real family tree, so you can have, say, well, we got it here. So we've got on the screen, there's you, and you have here 2 parent nodes, namely your father and your mother. This is looking at the mother's side family tree, as it hasn't shown the father's. So we can say that the mother has 2 parent nodes, namely grandmother and grandfather, and it goes on and on all the way up the tree until you get to like the start of the family. So you could see that they have two parent nodes. So if we write that out, family tree allows for 2 parent nodes. Although through the examples that we're going to see over the following clips and the rest of the talk for this, we're just looking at binary trees for now. Yeah, so I think that's all we need to cover for terminology and rules.
Specifically, not binary trees is this wrong terminology. It would be rooted trees.
A rooted tree, sorry, yeah.
Binary trees are what I'm going to cover now. So while technically these are binary trees, that's because they happen to be a special type. Binary trees are a special type of tree. And I really should give a small gap here. Are a special type of tree that allows for very efficient traversal and manipulation. Any tree can have any number. That's the wrong color. Can have any number of children. So this, for example, would be a valid tree, but it would not be a binary tree. A binary tree, and I have to delete this. I really should turn that setting off. A binary tree has at most a degree of 2. That's for the tree. The tree has at most a degree of 2, which means that at most there can be no node with a degree of more than 2. Visually, that means that you cannot have anything more than this situation here, and that can go on as it wants. But every node can have no more than 2. It can have less than 2. This is a perfectly valid binary tree, but it cannot have 3. There is special types of binary trees. For example, a perfect binary tree would look like this. This is a perfect binary tree because the height from the root across each of its 2 subtrees, and by the way, the height of the tree being the number of levels, also call it depth, the height of the tree is equal for both. There are various types of those. I'm not getting into all of them. We don't need to know, but generally, the closer you can get to this format, the better, because it is much more efficient, much more memory efficient, and also makes algorithms that manipulate it all the better. One other thing to keep in mind is that a linked list is technically a tree. If you have a linked list that is 1 to 2 to 3, then this is just a tree which has a root of 1, which goes to 2, which goes to 3. Everything has a degree of 1, but it's still a tree and technically still a binary tree. This format is when a tree is called degenerate. The tree is degenerated down into something like this. If you were to try to search for this tree using a binary search, which I'll do in a second, it would devolve into a linear search. Okay, so let me get this image up. There we go. If we're trying to traverse such a binary tree, here's an example. There are 3 main ways we can try to do it. And I didn't actually mention this. A traversal is when you visit every node of a data structure. So there are 3 main ways to visit every node of a tree. You have to start the root because that's how you access the tree. And they are called pre-order, and I actually color this. So red here, we see, I'll explain what this means in a minute, is called pre-order. we have yellow. I shall use this, I suppose. Yellow is in order, capital. Then we have green, which I have here, is post order. And what this shows here is it's saying that if you were to start at F and then go left, each of these, see this path here, each of these dots is forever setting you're in. If you're doing pre-order, that's when you add it to your list. So if we're going for pre-order, we're going from here, going down. We've now passed the red dot, so we put F on our output. Then we pass the B, so that's B in the output. Then A. And then following it along, we get D, C, E. Following back up, G, I, H. That's what you get for pre-order of this particular tree. If we're doing yellow, this is in order. This is how we put it in when we hit the yellow spot. That doesn't happen until we hit A. So we have A, B, C, D, E. Then we hit F, G, H, I. Because remember, we have to go this way around, so we don't hit this until we get to this point here, which is after H. F, G, H, I. And as a note here, this is alphabetical. That'll come up later. Then the last one is post order. It's on the right. That's A, C, E, D. Then we don't hit F till last. We do around here H, I, G, F. H, I, G, F. So those are 3 ways of traversing this type of tree. And this comes up in various different usages. Which one of these you pick helps you manipulate the data in the tree in different ways. The first of which is one of the biggest uses for a binary tree, which Elliot will cover, which is a binary search tree.
I'm going to move this up 1 second.
Yes, that's probably good. Oh, right. Oops. Yeah. They weren't supposed to be connected.
Just to be space efficient.
Right, that's
okay. So, like Cami said, we're looking at BST, which is a binary search tree. So obviously we're going to be using binary trees here. So we're essentially following a rule in the tree that new nodes are inserted to the left of a node with a greater value or equal to, and to the right of the nodes with less than the inserted node is called a binary search tree. So that's sort of the definition. So let's have a look at this. So left node with a greater value. So say if the root inserted to the left of a node with a value greater or equal than to the right. So we essentially can you put the picture in of the binary tree so we can look at this?
Yes, we'll do that
now. Okay, so in this one we can see. So to the left, so we have let's look at 20 just to start. So we're looking here. So we've looked at this, and so we want things to the right. We want it to the right of something less than of it. So we look at 20, and we get given the value 30. Well, we obviously know that 30 is greater than 20, so we insert it to the right of 20. And then we could say, namely, say we already have 20 and we get given 10, we insert that to the left. So we essentially are always going from the left to the right of the entire tree. We can also use this for, this doesn't have to just be used for numbers, we can use this for letters as well. So if we just look at this, say we have a root R, we say that if the next value is less than R, insert left, else if next value greater than R, insert right. And this makes it really easy to basically traverse it. So essentially now we can pick out going from left to right of the tree. So if we have that on screen a little bit more, just so it can be seen, the tree at the top. We can essentially go now from the left of the tree to the right of the tree and pull out all of the numbers in order. So we can start from the left. We can see that 10 is the leftmost node, so we can pull out 10. And then looking at the diagram now with not 10, we can see 20 is the leftmost node, and we can get to 20 going from 10. Then we can see that the next one's 30. We can get to there. Oh, there it is. And then we can see now that the next node, because trees are recursive, we can unwind on the stack and go back up here to 40. We can pull out 40. And then what we can do is go to 50, because that is now the next thing that will be leftmost. What we normally see is in here, it's these 60 and 50 look nearly in line. If we follow the line down, 50 is slightly more to the left. So we can see that it's 50 first. Then we look at 60, pull out 60. I'll just go to the side here. So now we can see that we've reached the root, but we can still access the right side of the tree because we've already accessed everything that's left of the tree. So then we can follow it all the way down to the bottom. The leftmost node coming on the right side is 70. And then 80. We can get to 80. And we can get to 90. Follow all the way down to get to 100. There we can go to 110. That's the next most left. And then finally 120. And that's essentially how you traverse the tree. So always picking the leftmost node given the scenario. And like I said before, say if you have a scenario where you've got 30 back there and you've already been to 20, you'd have to go back through 20. Well, it's recursive, so it will just unwind on the stack back to the next node that hasn't been traversed. If you think of it like in an algorithm, you'd have some kind of like way to show that this node has been marked as traversed. So you just basically have a check, say if traversed, leave it and unwind. It's pretty easy like that. What's next? Expression and evaluation. Is that you, Cami?
Yes. Oh, another point on BSTs that I forgot to put in the notes is that one of their greatest usages is searching binary search trees. So if we had the value 50 and we wanted to figure out if 50 is in the tree, then because we know 50 is less than 60, we can discount the entirety of this section of the tree because we know it has to be on the left. So we can immediately go left to 40. Then 40, well 50 is bigger than 40, so we can go right. And then if at this point there's no 50, then we know 50 is not in the tree. There is 50, which there is, we know 50 is in the tree. Most other searches require a lot more than just 2 steps. So searching with a binary search tree has a time complexity of O of log n. It's one of the best searches you can do. It might be the best, I'm not sure. And similarly, if you're trying to insert into this data structure, for example, if you're trying to insert 5, then it is 5 is less than 60, go left, 5 is less than 40, go left, 5 is less than 20, go left, 5 is less than 10, go left, and then insert the 5. And that's how simple it is to insert as well.
Yeah, I think it is. I think it is the best. Fair enough.
Though a note about inserting into binary trees, if you did a lot, say you added then a 4, and then a 3, and you kept doing that along, this tree is getting very unbalanced, and binary trees are their best when they're the most balanced, specifically because of the property of searching them. If you had a tree that's mostly like this, that's a lot of steps you can repeatedly go down. That's not log n anymore. So they're log n when they're perfect, when they're properly balanced, and they have as little variance in height as possible. This tree, as it stands with this extension, is not balanced. The height of this is 1, 2, 3, 4, 5, 6, and the height of this is 3. That's not very good. really you want to be a difference of 1 at most. Okay, moving on. Okay, this is one of my favorite things in computer science. The first thing I found that I really, really got excited about. It was such an interesting algorithm. And this is how you can evaluate expressions. So if we have the expression g equals 1 plus 5 minus 3 to the power of 3 minus 1. And we want to write some code which can evaluate this. What is the method we can go about? And let me, that's quite difficult. But the great thing about trees is that we can make that quite simple to do. The idea is we want to store this, and I just need to get my notes in a bit of a easier to read format. One moment. Zoom in. There we go. Sorry about that. There. So the idea is we want to rewrite this in a way that can be interpreted. The problem is with doing this evaluation is that order of precedence is a thing. You have your BODMAS, or whichever of the several you want to use. This has to happen very early. We can't do anything until this has happened, but we can't do this until this has happened. So we can't have 3 to the power until we calculate what 3 minus 1 is. So that means this has to happen before this, but then this has to happen before this, and then all of that has to happen before we can assign the equation. So ultimately, what you need to do before you can do all of this is figure out the order of precedence for this equation. This is also why it's very difficult to do this in a single pass just to evaluate it, because you need to add your implicit brackets. Because, for example, there's implicit brackets here because this has to be done before anything else, by virtue of it being in here. So let's rewrite this according to that. So what's the last thing to happen? That's the equals. So we're going to write that as equals g equals, then everything followed by the brackets. What's the next thing to happen? So the second to last thing to happen. If you look through, it is this minus. This minus has to care about what this equals and what this equals. So this is the next thing to happen, and it cares about what's in here and in here. I'm going to give me that much room. I hope I don't need more. On the left of this is 1 plus 5. So this has to be evaluated for this we can do. And it also needs to evaluate everything in here. I'm going to use a different color here as well. It's 3 to the power of whatever these brackets evaluate to. And then it is 3 minus 1. So they're all the calculations we have to do. And we also have to do the entire thing. And the process is, once you've turned it into this format, surrounded by brackets, it's actually very simple to calculate what the tree is going to look like. Because you just remove a set of brackets. So these brackets get removed. Now we have blue equals. This is the root. This is the last thing to be done. The left of equals, its left operand is g. We have g over here. And its right is the next thing to be done. So now we can delete this. Next thing to be done is this minus. So we go down, we have a minus here. Perfectionist in me says this has to turn into a circle. I give up. Perfection in me is not very strong. Left of this is this evaluation. This is a plus, so we have to have a plus done here. Why am I in green? Plus over here. Okay, now it just doesn't want to work at all. Plus has to make 1 plus 5. 1's on the left, so 1 goes over here. 5 goes over here. But now it wants to work. And then I'm running into the problem that always happens when you draw trees, is that this is going to clash into itself. Yay. Okay, next operand. Let's clean this up. We have done this, we've done this. We know this is what's left, we know this is what's left. Next up, that needs to be evaluated second to last is, second to first, is this. So we do to the power of, and a bubble. Then we have 3 to the left. And to the right is this 3 minus 1. This is minus, so to the right of this is a minus symbol. And to the left of that is a 3 and a 1. So now we have the expression tree, that's what this is called, for this equation. And we want to be able to read it. In fact, there's a fair bit of empty space there. I'm going to move this up to there. So this is the expression tree for this expression. And in practice, what you might want to do is rather than have direct values 1, 5, 3, 3, 1, you would want variables. So g equals a plus b minus c to the power of d minus f minus e. However, for simplicity, I didn't want to have a table saying this is what these values are. I do actually want to get a number out of this. So I've put actual values in. It would work just as well if you had variables with a lookup table. Okay, so there's that process. And now we want to actually be able to turn this into a value. So what we do is we have to work with a stack. If we have a stack such as this, what we do is we go through. Oh no! I've missed a step. Apologies. First, we have to actually get an expression out of this. This is for converting between different types of notation. This is a notation everyone knows, but it's not very good because I said it has brackets, and brackets screw up everything. There are 2 other types of notating mathematical expressions. This is prefix and postfix. Postfix also is called reverse Polish notation. So postfix, reverse Polish notation, is, for example, for this 1 plus 5 would be 1, 5 plus. You put the operator after the operands. And then we have prefix. And this would be plus 1, 5. So you put the operator before the operands, like this. And infix is when you put it inside. And let's see, infix equals 1 plus 5. We want to get it into a format that doesn't have any precedence rules, because we have to deal. We want to be able to figure out what the answer is by going left to right. And we're going to be doing postfix. Now, if you want to do postfix, what you want to do is traverse the tree in post order, which is when you hit the right side of a node. So we're going to go through this tree and get the output when we go through the right side of the node. And I will use green for this. So we go through. Actually, before we do this, if we have a line, this is what line we're trying to hit. When we pass this line, we add it to the output. There. So we're going through from the root to the left. Up here, we've hit G on the output. Going around, not hitting anything. Now we've hit 1, 5, and plus. So we have 1, 5, and plus. Going around again through here, we've hit a 3. We've hit a 3, a 1. So a 3, 3, 1. Minus, power of minus, minus, power of minus, and then equals. So this is the postfix expression. Let me just double check that's correct with my notes. 3, 3, 1, minus power. Yes, good. Always good to see that. This is the postfix expression for this infix equation. That mathematically exactly the same, but this is much easier for us to compute with. So now we switch over to using a stack. And the idea is we'll go through this, and whenever we hit an operand, whenever we hit an operand, which is one of these, we will put it in the stack. When we hit an operator, we will take the 2 things from the stack and use it as the arguments for that function, plus or power of or whatever. So we go through, we put G in the stack, we put 1 in the stack, we put 5 in the stack, then we get a plus. So what we do is we remove 1 and 5 from the stack, and we get a plus 5 and 1. What's 1 plus 5? That's 6. We put 6 back in the stack. Now we have 3, 3, 1. So 3, 3, 1. We've hit a minus, so minus. Then we've got a 1 and a 3. Take them from the stack. Now 1 minus 3, that is 2. Sorry, 3 minus 1, that is 2. Going on. Now we've hit this. We are over here at the power of. We take 2 out. We do power of 2 and 3. So 3 to the power of 2. That is 9. 9 goes on the stack. Need a bit more room. Next up is negative. So we have negative 9 and 6. This is negative 3. Negative 3 goes on the stack. And then equals negative 3g. So now g is equal to negative 3. Through this, we actually have a set algorithm for figuring out what the result and evaluation of an expression is. And using this, I really love this way of being able to do it, and the fact that this is a diagrammatic way of converting one type of fix notation to another. You can also do it using a stack. In that way, you can do it in a single pass rather than this, because turning this into that version with all the brackets, which for completeness' sake, for anyone looking at these notes, I will put back in from my notes. Let's put this over there. Or there. That works. Is very useful. Being able to do it in a way without having to construct the graph, because they're somewhat complicated. However, getting your head around it, I really like this graphical way. And the fact you can do this all is just awesome. Like, computers can actually just, hey, here's an equation, let's solve it. And one of the things you need for this is knowing order of precedence rules. You need to be able to figure out what the order something has to be in, and then be able to extract that out. Not making an actual solver for this that takes in a thing as a string and then solves it and gives you the numerical output is a nice little programming exercise that people may enjoy. Is that everything for this section? Let me check my notes.
I think so.
Yes. Yes. So, on to graph terminology
Right.
with Elliot.
What am I doing up to here now? Am I just doing up to which bit?
If you want to take up to cycles.
Cycle? Okay. Right. Okay. So, for a graph, there's a couple of different things we need to settle before we go into looking at what you can do with a graph. So, let us do that as we go. I'm just going to move some things out the way as I go. So, first of all, you can have two types of graphs. So, I'm going to tell you about some of them and I'll draw some out for you. So, we have, first of all, an undirected. So, an undirected graph, all edges are bidirectional. So, that'll be undirected. All edges bidirectional. And any edge can be traveled along in either direction, that means. So essentially means both edges, you need to think about it, you can go from A to B and B to A, and like when you have a pair, they're not like ordered. So what that would look like is, say, if you have it in set theory, so you can have two sets to represent this. I think my things just started lagging. Yeah. So we can have two sets, one of nodes, so, and then we can have one of unordered pairs. Now, what this means is we can have something that looks like this. So we can have let me move some of this around. So this could be a graph here. So we'd have the set here. The set here of nodes. So A, B, C, D. And then we'd have a set of pairs that connect one edge to another. And it literally doesn't matter on the order of which the pairs are in. So we've got A to C, D to C, C to B, and B to D. And I think that's all we need. So this would be two sets that represent this graph. And this graph could look like any way you want it, basically, as long as it satisfies these conditions. This is just one way of drawing that graph. And we also have directed graphs. So if I directed. Now, these are a little different. So these allow for directed edges. And now this changes how we think about this in set theory. So we can still use two sets. And we can still use one of nodes. And now our second set, order matters. So it would be ordered pairs between nodes. Now when I mean order matters, I'll show you now. So let us draw another, well, we'll use the same graph, but I'll redraw it over here because we're going to need to put some arrows on the edges. So we're going to have A, B, C, and D. Okay, and then we're going to have A going to C, C going to D, B going to D, and then what else do we have? We had it between there. Oh, we'll also just say B goes to C. Now what this means is we have two sets. So we'd have the set again, A, B, C, D. And now we have the set of ordered pairs. Now what we mean by this is, it's in the order of which you would, that the arrow flows. So for this we'd have A to C. So the first in the pair being what node you're coming from, and the next in the pair being what you're going to. So if A to C, C to D, B to D, and B to C. Okay? So if I just put a little bit notation here, so we have V and E, where V is node coming from, E node going to. Okay? So that's a directional graph, or directed graph. Now, I think next we need to look at weighted graphs. So I'm just going to move all the stuff down again. Well, you've got it. So we've got weighted graphs. So weighted graphs essentially mean that each edge has a weight on it, I'm pretty sure. Yeah, each edge has a weight, and that denotes the cost between traveling from one node to the other across that edge. So let's have a look. So we'll try out the same graph, but this time we'll give them weights. Just for this example, we'll use a undirected. So we can see that each of these edges now have a weight. So if we want to travel from A to C, well, that's going to have a cost of 4. And this essentially means go from A to C is 4. So say if we wanted to go from A to D, well, we'd of course have to do A to C, and then we'd have to do C to D. You can see that this cost is 4, this cost is 10, and the way that we can literally just get the cost of traveling from A to D is adding those up. So this gives us weighted graphs, so just weighted edges. Yeah, so that's fine. Now let's look at the degree. Let me just move. Can you move some stuff out the way for me, Cami? That's it. So we look at the degree. The degree basically has the same definition of trees. So the number of edges that come off one node. So let's just have a look at this on an undirected for now, because directed can be a little bit different, and we can do some certain things with directed graphs. So let's look at undirected. So we have the same thing, A, B, C, and D, with there, and there. Okay, so we got all these. Now degree, let's have a look at the degree of some of these nodes. So let's have a look at A. So the way we can show degree is basically denoting with the deg function, I'm going to call it. So we use deg of A, and we can say this is equal to just 1 for A, as it has one edge coming off it. You can say deg of has 2. Similarly, deg of D also has 2. And then lastly, deg of C has 3. I hope this is fairly trivial and I don't have to show, for this case, what's going on. You can see that the number of edges coming off each node. But we can also do something different for directed trees. So we can do something called in-out degree. And so let me just show you that now with one thing that we can do. So let's create the directed tree again. Okay, so we got this directed tree here. Now what we can look at is different degrees of edges going in and out. I'm also going to quickly add a couple more edges here, just so it makes looking at this a little bit more easier. So let's look at so we got our nodes here, and we got the create a little table here. So we got in degree of n, and out degree of n. So let's say we've got A, B, C, D. So let's look at the in degree of C. So what we're looking for here is all nodes that are going in, all edges that are leading into this vertex. So let's have a look. So see, it's got 2 arrows that are associated with it, namely AC and DA. Quick way to tell if it's an in degree is the in a pair. So we have a pair here. We can say that they're ordered pairs. So if we know that this is going to, this is coming from, we can say that the second one here, well, this is going to. So if you had the set of ordered pairs, but you could just count up how many times that A, for instance, appears in the right side of the pair. So we can see that just by looking at the graph, there's only one thing that goes into A. So we can say A has an in degree. I've just zoomed all the way out. 1 second. Has an in degree of 1. And then B, so we're looking at B now. This just has an in degree of 1, 2. And then C, we can see C has an in degree of 2. And D also has an in degree of 2. Now, out degree is probably what you would guess, the number of edges leading away from a vertex. So let's have a look at this. A again is 1. B is also 1. C is, I think, is also 1. It's just zoomed me out all again. C is also 1.
B and C are 2 because they go to each other. Bidirectional.
Oh yes, sorry, I didn't see it was bidirectional. Yes, so that's right. So I didn't see this arrow in the middle here is a bidirectional, so they're both 2. And then D has 1 as well. So here we can see now in this table that you can see all the arrows going in and all the arrows going out, which can really help you form a graph. And what we also want is that both different columns in the table always sum to the same number of edges. So we can see here 1 plus 1, 2 plus 2. Well, you can see that is 6. And then 1 plus 2 plus 2 plus 1, that's also 6. They're equal each other, so that means we have all of the edges, or at least both of the edges are the same, so we can assume that we have both of the edges if we've made no mistakes on both sides of the table. Okay, so I think that's all we need. We can also say that a self loop adds 2 nodes to a degree. So something like that would add, so say you would have C going to C. Well, that makes, so if it's going into C, so 2 nodes to a degree. We can say that the degree of C then, if you have an undirected, would be, if we amend it for the sake of having our new value over here on the left, we can amend that now to be, so it was A to C, B to C, D to C, and then C to C. So C comes up 1, 2, 3, 4, 5, so then the degree becomes 5. And then with the directional, you just changed the in and out degree. So you'd add an in and out degree to like 1 each side. So in this case, it will become now because it's going out of C and into C. It doesn't need a bidirectional arrow because it's only going to itself. So that would be a self loop. And now we can look at simple graphs versus multigraphs. Let me just grab my notes for this now. Don't know if I personally had notes on this, but I'm going to have to quickly read. Can you do this bit, Cami, for me? Simple graphs and multigraphs? I didn't have notes on that myself.
Yes, give me 1 second to put these forward a bit. Should be enough. Where's the notes on simple graphs? Oh, yes. Simple graphs. Well, a graph is simple if it does not contain any loops and it does not contain any multiple edges between the same nodes. So, for example, if we had A, B, C, always one, D, and we had this, I'll go undirected for simplicity's sake. this is a simple graph. If we had this, that wasn't what I was having for. If we have this, then this is now a multi-graph because we cannot have loops. And similarly, if we had this, this is also a multi-graph because it has two edges between these two. If this was directed, then it would have to be something like this, where both are going in the same direction. So in simple graphs, you don't have to worry about the possibility that there are multiple of the same edge. Example why you would want that is if they had different weightings. This was 4, this was 3. You want to represent there's two different paths of two different weightings. If for some reason you wanted to keep both, there are situations. In those situations, they're all multi-graphs. Otherwise, it is simple. And similarly, if it is called a multi-graph for undirected. Otherwise, it's called a multi-digraph. Digraph, I don't think we've actually mentioned this. Digraph is the shortened word of directed graph. So it's a multi-digraph if it's a non-simple directed graph, or as it's just a multi-graph for undirected graphs.
Okay, so next we have subgraphs. So I think this concept's pretty intuitive, but we'll go over it pretty quickly. So we have, let me change my color back. We have this graph I'm going to draw out here as just going to use an undirected because it doesn't really matter. We can illustrate the point with this. So we have this this graph here. This is what we're going to call this. Have I just drawn a line across the whole thing? So we have this as graph 1. I'm going to draw another graph now. What's really annoying me? I did something stupid. So we have these two graphs here, and I'm going to call this one graph 2. We can say that 2 is a subgraph of 1, and 1 is a supergraph of 2. So 2 is a subgraph and 1 is a supergraph of 2. Now, how can we see this? Well, we can literally just see by visually looking at this that 2 contains, if we were to put this in a set theory style way, it contains all the pairs in 2 are also contained within 1. So let's write this out as set theory. So graph 1 has A to B. Oh, something went on there. A to B, A to C, B to D, C to D, C to D, and C to B. And then we can see here in this set, we have C to D, C to B, and then B to D. Now if I highlight this, we have C to D, we have C to B, and we have B to D. And this is this set here. So we can say that, yes, indeed, 2 is a subgraph of 1. And then similarly, 1 is a supergraph of 2. Okay? So then if we move on to paths, I'm going to give a quick definition of a path. Once I move stuff out of the way. Won't let me move stuff. Oh, did you already move it? Oh, you did. Okay. So a path, let's give this a definition, if I can find it on my notes, is a path is a sequence of vertices in which each pair, let me just wait for my thing to catch up, each pair of successive vertices is connected by an edge. Now, this is quite a big definition, so we'll look at this visually. So we can have the path on the graph undirectional, just for the sake of simplicity. You can also do this with a directed graph. So we'll just draw this here, 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 here. Okay. So let's say we have the path in the set. We have A to B, D to D, and then D to C. Now this is one path of getting from A to C. So you can see we've gone here, here, and then up here. That would be the path. And so this can have a number of attributes. So we can say this path has a length of 3 as it passes 3 edges. We can sometimes say the length refers to the weight of the edges. So let's say, let's just call this an unweighted. Let's give it a weight. So 4, 3, 8. So you can say now, underweighted, it's a length of 4 plus 3 plus 8, which is 15. Okay, I hope that makes sense. And I think that's all we need to know for just the basics of a path. We can also have something called a cycle. So a cycle is a path starting and ending at the same node. And we'll use vertex actually, because we've been using vertices the last 2 couple definitions. So we got starts at the same vertex. So what this means is we've got the graph here again. Let's say we had the path A to B. I'm going to make this directional just so it illustrates a point. A to B, B to D, and then D to A. So now what this means is we have this path. Goes here, and then goes here, and then we go up here. So as we can see, this now starts at A and ends at A. So now we can call this a cyclic graph. And we can also say that a path, a graph is, a path is acyclic if it contains no cycles. So we could say a graph is cyclic if it contains more than one or more cycles. Acyclic if contains no cycles. Okay, and now I think I can hand it over to Cami for simple paths.
Yes. In fact, before I do that, I will just push a bunch of these down a bit.
Mm-hmm.
Push. And push. There. Okay, so a simple path is a path that does not contain any node more than once. So if we have a graph such as this, apologies about the number of graphs we're drawing, by the way. I had intended to pre-prepare some, but writing the notes file for this took a lot longer than I thought it was going to. I didn't get the chance. So if we have the path here, then we have a C over here, and then an E over here. I think that will illustrate the point. If we can go from A to B to D to E, for example, and then maybe all I'm doing is to illustrate the path rather than drawing out the set. This path is a simple path because it does not contain any cycle. If this path included this, so it went A, B, D, C, E, D, then it would contain a cycle. It would, even though it doesn't end at the same position, so it itself is not a cycle, it has a sub-path inside it, which is a cycle. So it is not simple. So a simple path is so any path that does not contain any node more than once and does not contain a subpath that is a cycle. Yes, yes. Another type of path is a Euler path. Almost said Euler then. An Euler path is a path that uses every edge of a graph exactly once. So we have A, B, C, D, E. And we have, for example, this to this to this. And then we also have this and this. We would try to find an Euler path through this, we wouldn't be able to, because you cannot go from A, you cannot access this and this, because there's no way to get back to A. If there was a way to do this, for example, rather than having this edge, then you could go A, B, D, back to A again, to C, to E. That would be an Euler path through this graph, because every edge was visited at least once. A special type of Euler's path is called an Euler cycle. This is when you start and end at the same node. So an Euler path, I'll put this here, uses every edge cycle path that ends where it started. Another type of path is called a Hamilton path. So a Hamilton circle. A circuit. Oh, I don't think we mentioned this. Oopsie. Did we? Let me just double check. A Ooh, there's a lot in this section. Similarly not. I can't find it. There, cycles. Another word for a cycle is a circuit. Equally, they can be interchanged just as much as node and vertex. So a Hamilton cycle, in fact, I'll put this here, is a cycle containing every vertex exactly once. Ooh. Same goes for Euler. Has to use every edge once. Hamilton cycle has to use every edge or every vertex once. So Hamilton cycle uses every vertex exactly once. I'm not going to draw a graph for this because while it's fairly simple to produce a graph or to check if a specific graph has an Euler cycle in it, it is very difficult to figure out if a graph has a Hamilton cycle in it. This is considerably harder, and I think is an open question. We're trying to still find the answer to if there is a guaranteed way to determine if there is one without brute forcing it. Okay, connectivity. Where's my notes on this? Okay, so this is different depending on if you're dealing with a directed or undirected graph. For undirected, it doesn't use a capitalization there. An undirected graph is connected if there is a path between every pair of vertices. So it is, that's an M. If there's a path between every pair of vertices. Nodes. So, for example, if we had A, B, C, D, we have this. If we had this and then this is not a directed graph because there is no vertex between A and B, unconnected graph. If there was something like this, there was the same thing, A, B, C, D, and there was something like this is a connected graph because from any node there is a path through which you can get to every other node. They don't have to be directly connected, so this would be connected just as this. You don't have to have a node between every single one, just a path. For directed graphs, connectivity is a bit more specialized. Directed. So in digraphs, a digraph is weakly connected or strongly connected. So if there is a path between every unordered pairing, between every unordered pairing, it is weakly connected. If it is every ordered pairing, it is strongly connected. So if you have a graph, for example, again, we can use this, A, B, C, D. I also have it here, A, B, C, D. So it does path between every unordered pairing. So if you have this, and then this is weakly connected because from every node you can get to every other node if it were undirected. The reason connectivity is useful is that if you had, for example, a graph which had two separate parts, so you had, I'll just do circles rather than letter them. A goes to here, goes to here, goes to here, and then another bit over here, which goes to here, goes to here. This is an unconnected graph because it has two distinct groups, which sometimes is useful, especially in stuff like we've done in 109. Yes, 109 with orderings and equivalence classes and such. Example of this is if we had this, choose this, choose this. This is still weakly because you cannot get from D to E. If these were all, for example, like this, now it is strongly connected because from anything there is a path to every other vertex. I think last is saturation. Yes, saturation. Saturation is a concept based on how many edges there are in a graph. So a graph is highly saturated. In fact, I'll just say saturated. Is saturated. This is a scale. So a graph is saturated if there is. Why did I say fully? Fully saturated if there is a edge between every vertex. So this means that if you would have the four things we had before, 1, 2, 3, 4, we have this. This is a, why the hell has it done that? Is a fully saturated graph because from every edge, from every vertex, there is an edge to every other vertex. You can get from every to every in a single path of length 1. Alternatively, you have a sparse graph. So a graph is sparse in the opposite case. I'll use it in the opposite case rather than rewrite the whole thing, but with a single word different. In the opposite case. So if we had this, 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 and this is a sparse graph. It's a scale. Most graphs are somewhere in between sparse and saturated. Nice line. So some graphs will be somewhere in between this. This is very important for what's coming up next, which is how to store. All the way to the top. There we go. How to store graphs in data. Because having the set theory notation is very nice and for manipulating and stuff. Most of the times you don't want that because sets have various disadvantages when actually stored in memory. You usually store them as some other data structure. For graphs, there are 3, and they're slightly different for each one. So I shall draw a graph. In fact, I think, am I good? Do I have a version of these for all of them? No, damn it. Okay. So we have a graph such as this. We have A. Oops, wrong color. A, B, C, D. That's not a D. E, F. Then we have a line here. I'll start with an undirected graph and how to store that, and then move over to a directed graph. So we're trying to store this graph. There are 3 ways to do this. I will first show the first 2 and then go into the third one at the end. The first is called an adjacency matrix. And the idea here is that we make a matrix of all of the nodes. So A, B, C, D, E, F by A, B, C, D, E, F. And then you put a 1 if there is an edge between the 2 things at that cell. So there is not an edge at A, it does not have a self loop. So it is 0. Simply none of these have self loops. So it's a simple graph. So put it down the diagonal and put 0 all of those. There is from A, we have 1 to B, we do 1/2 to C, 1 to D, but not E and not F. For B, it is just A. We do not have 1 to itself, or C, or any of the others. For C, we have 1 to A, and 1 to F and E. For D, it is A and E. For E, it is C and D. And for F, it is just C. Now, when looking at that, what you can see is that this is symmetrical. If we look along down this diagonal line, this mirror line, we can see it's completely symmetrical. This is true for all adjacency matrices. They will always be symmetrical because for everything going one way, there has to be one going the other way. And secondly, you can see that there are 1, 2, 3, 5, 6, 12, so 24. 12 things, so 36 zeros in this matrix. Just saying that there's no data here. It's very, very inefficient for memory, for this graph in particular. So an alternative to this, rather than have all these zeros everywhere, which is just saying nothing to see here and taking up memory, we do an adjacency list. An adjacency list is just saying, well, rather than having zeros, why don't just have references to these instead? So we have A, B, C, D, E, F, and then A, well, A is going to B, C, and D, so it's B, C, D, direct references. B goes to A, C goes to A, D goes to A, B and C go to E and F, D goes to E goes to C and D, and F just goes to C. So now we have cut down the amount of data we're storing significantly. However, we still do have the repetition. We have, for example, A going to B and B going to A. It's an undirected graph, so we would like to be able to get rid of this because it's superfluous. Now, if we want to be doing, actually, I'll give this a title of undirected. If we go into a directed graph, I'll do the same thing, but add in arrows. Oh, yes. If we're looking at the time complexity, and in fact the space complexity, I'll rewrite this in a second. So the time complexity of this, if we're looking at access, we're trying to see is there an edge between these two, is 1. It's a map, it's a hash map. There's plenty of ways you can do this, and access is always 1 if you're doing it in a proper way. You want to look at A, B, we just look at A, look at B, there you go. You don't have to look at anything else based on how big it is. For adjacency list, lookup is going to be O of n because it's typically they're done as linked lists. Either way, you have to go through the full thing. You have to do a search. So it's going to be O of n, which isn't very good for a thingy. However, if you look at the memory cost, this is for this n squared, and for this it is also n squared. Doesn't look it, but since it's bigger notation is worst case scenario, then there's a possibility you will look at an adjacency list. You will make an adjacency list for a fully saturated graph, and worst case scenario, that is the worst case scenario because every linked list will contain a 1, or rather, if you're representing this, every cell will contain a 1, which means that every linked list will contain every other cell, every other node. I mean. The reason for this, and this is an example where big O is bad, is that this is inaccurate. Specifically for these two. Why is it going white? Okay, that was weird. Yeah, so specifically, n squared is inaccurate, as is n. Because in reality, you're never actually going to be using it like this. Pardon me for a second. Mute that. You're never going to be using adjacency list on a saturated graph. They are for sparse graphs, and adjacency matrices are for saturated graphs. There's exceptions, but typically using sparse graphs. And even though this is showing that adjacency lists are clearly worse because they have worse time complexity and the same memory consumption, in reality, on a sparse graph, they are many, many times better. And on most graphs are sparse. The majority of the time, a graph will have less edges than nodes by a significant margin. Only a small fraction of the entire thing will be about the connections. common example of this is Facebook. How many people are in the world who use Facebook, and how many of those people are friends with each other? If you're trying to make a graph of all friendships, you're going to have many, many more users than you have edges between them. The degree will be low. Or the average degree will be low. So this is an example of don't just blindly follow big O. You have to look at average case, look at best case, and actually figure out which of those you fall under. For this, big O for these aren't something you should follow, or outside of very specific circumstances. Okay, directed. That's not a circle. Why is it when I want it to work, it doesn't? Okay, directed. Similar thing. We are going to be doing the same graph. So a it's a bit easier. That wasn't where I wanted that. Haha. Okay, we want to manipulate this to be a directed graph, so we're going to say this goes to here, this is bidirectional, this one goes over here, this goes to here, and then to here. And then for an example, we're going to make this be a loop. Okay. So, if we're making the JC matrix again for this, we have your A, B, C, D, E, and F. A, B, C, D, E, and F. A has nothing to itself. It has a 1 to B, it has a 1 to C, and a 1 to D, and then nothing. B has only to itself. I'll put this in. So on the other graph, we had the diagonal be all zeros. Now we have a loop. We actually have a 1 in that position. C goes to A, it goes to F, and that is it. D goes nowhere. E goes to C and D. And F goes to nowhere. Once again, a whole lot of zeros, even more than last time. What we see here is that it is no longer symmetrical. And there are in total less ones because there is less data in the graph technically, because you cannot go from F to C as before you could. If we were to draw the adjacency list for this, then it would be in fact, I'll just draw it at the same height. This one goes to B, C, D. This goes to B. This goes to A and E. This goes to nothing, so nil. Nice consistent use of capitalization there. This goes to C and D, and this goes to nil. Yes, that is correct. Good. So even less data here because there's less data in this particular graph when it's directed versus when it's undirected. But again, we're still getting on this A going to C, C going to A thing. We have duplicate data, and we would like to avoid that. That's where the third type comes in, and this is called an incidence matrix and an incidence list. And for this, we're going to have to label our things. Oh, also, before I move on to this, so I will just copy paste this over here. First try. If this was a weighted graph, so for example, if the cost of C to F was 5, was 5, then rather than a 1 on C to F, I put C to E. Oops. Rather than a 1 here, you would put a 5 here if it was weighted. And that goes for all of it. 1 is if it's unweighted. If it's weighted, you just put the actual weighting in, and that works. Okay, so I need to manipulate this. So now we have these different path labels. However, one thing we're going to have to do is split this one into two, because the way these work, you cannot have a bidirectional arrow. You have to have two arrows going in different ways, two edges. Okay, you need to label these. This is going to be a 1, 2, 3, 4, 5, 6, 7, 8. And again, keeping that for an example. The way this works is, rather than the matrix being nodes by nodes, it's nodes by edges. So we have the nodes on the top, A, B, C, D, E, and F, and then we have 1 through 8 at the bottom, referencing each of the different types of edge. Not different types, but each of the different edges. 7, 8. And then what we do is, if we have A, for example, A has a 1 connects A and B, on the 1 row, we put a 1 on A and a -1 on B. This shows that it originates at A and terminates at B. So essentially a coordinate. Where's it end? Where's it start? Where's it end? That's -1 ends. I'm not going to put zeros. Imagine they're zeros. There's no point wasting time. For this one, A to C, you have a 1 on A and a -1 on C. This is why we had to have two separate ones. You could do 1 and 1, like this, which to me makes sense, but people who made it said let's not do that. 3, this is a -1 on A and a 1 to C. 4 goes between C and F, so we have a 1 on this and a -1 on that. 5 is this one, so we're between E and C. 6 is E and D. 7 is A to D, and 8 is B to. Yeah, so this is the thing with incident things. You can't have self loops, because you could just do 1, which is what I would do if I was designing something to implement this data structure. Is I would just put a 1 there and have a small check in the thing to say, is there only 1 with no matching? Oh, it's a self loop. In the official thing we're doing for the module, though, you're not allowed to have self loops. These only work for simple graphs. No self loops. Doesn't work. Well, you could say there is one. I think the official way of showing a thing is to lose the information. You just put zeros across the entire row. And you can say there is a self loop, but you have no way of figuring out where it is. Which is why, for me, it seems obvious just to put a 1 there and say, oh, there's a self loop on B. But, for some reason, that's not allowed. And I think that's everything for representing. So, on to the last thing. Thank you for sticking with us. We know this one's lasting a bit longer than usual, which is searchers of graphs.
Okay. So, we'll quickly go over the different searches of graphs. Anyway, my whiteboard's just crashed a second, so I need to load back in. There are two different types of searches that we're going to do on graphs, and they can use two different data structures to help us show how we traverse the graphs in a way that matches the algorithm of the search. And I will let you know once I load into the whiteboard, which is taking forever.
Do you want 2 of those images, by the way? 1 for each of the 2?
Yeah.
Okay.
Yes, please. Why is it taking forever for me to load in?
By loading in, is there anything else we need? I could go into a bit more detail. Ooh, that section was big. I think we covered everything in a good amount of detail. So this is a question we can cover while we're waiting.
Actually can't load in.
Oh, this is not good.
Let me reopen the app. Right, if I can't load on this one, Cammy, you'll have to take it.
Yes.
And I'll probably go because I've got to be somewhere. Give it a minute. Give it till 1:45 and then.
I don't have notes on this, so if you could pass me yours.
Yeah, 1 second. I literally only have screenshots of the lecture stuff.
That's fine. It's just to get the rough type of thing. If it's anything specific for BFS and DFS.
Second.
I'll put a chapter in the video to say this bit's technical difficulties, so you can skip to the end of it for anyone watching. Okay. Okay, so we're working with a Q.
Right, I don't think it's letting me loading in, so I'm gonna have to head off.
Okay.
Right, see you in a bit.
Yeah. Okay, 1 moment, and then I shall, while I refamiliarize this myself.
Alright, take your time, mate. I'm still here.
Okay, so implement these. Okay, so it's just implement depth first search and breadth first search. Let's see if I can remember them off the top of my head. So breadth first search is the first one. Breadth first search, the idea is that if we're starting at A, okay, so we're going to start at A, and I think we're just going to search for everything. I see. So the way prudence is done is we're not searching for anything particular. We are just searching for, we're just searching the entire graph, trying to traverse using this algorithm until we've searched everything. Exhaustive search. Okay, so we are going to try and start on A. So we are looking at A and we're trying to go from A everywhere using breadth first search. Now, breadth first search follows the principle of breadth before depth. You should explore everything at the same depth, path length from the starting position before going any further. So you, for example, if you explore B and discover F exists, you shouldn't explore F until you've explored both E and D. And we'll be doing this using a queue, which is a form of linked list. So if we have what we know, this is what we know about the graph. We're starting at A, and all we know, A exists. We have no idea what the rest of it looks like. Obviously, we're using a visual, so we can see it, but algorithm doesn't. So we have a thing, we're going to call it frontier. This is going to keep track of what we know and have not yet explored. So we start off with A in the frontier. Like so. And we explore A. A is connected to B, D, and E. So now the frontier will contain B, D. That's not a comma, that's an E. Comma, E. Then what we want to do is keep track of the things. And in fact, truly, we should be doing this. Shall I? Okay. Since this is a queue, I'm going to specifically go over this like this. So if we have A, so we have a head. Imagine frontier is pointing at the head of the list, which is currently A. We explore A, and what we have left is B to D to E. So we have this linked list, which is acting as a queue. We were trying to do from left to right, and that's why, because queues will process the things that have been there longest, and the things in this algorithm that will be there longest is the things that have not yet been that were found the longest to go. So we explore A, we get this, this, and this. if we explore B and discover F, that is newer than D and E, so we know for a fact, using a Q, that we'll explore D and E before F, which is the whole principle of this algorithm. So now we have B, D, and E, and I'm just going to start from now on, show what the algorithm looks like this rather than rewriting frontier. We will explore the front, that is B. That will then do D, E, and then I'll put what B finds at the end, which is F. We'll explore D. D will discover H. Not H. We'll discover E, and then put append H. Then we'll explore E. That will go find F. We already have F, so we'll ignore that, and it finds K and G. So we have F. Yes, F, H, and it finds K and G. K, G. I shall move down a bit and move this here. In fact, I'll just move all this up so we're not wasting space. Up we go. There. We'll explore F. F will discover C and K. We already know K, so only that gets there. So K, G. F will discover C. K is already in it, so we'll ignore it. We'll search H. That tells us nothing. It's a child node, essentially. It has nothing we have not yet explored. That leaves us K, G, C. We now do K. K is here. K doesn't give us anything new, so we just G, C. G is here. It doesn't give us anything new, so that's just C. And C doesn't give us anything new, so that's the end of it. So through that, we have searched the entire graph exhaustively. The alternative to this is, rather than a queue, we can use a stack. A stack works on a different principle. Rather than first come, first served, it is first come up, last to come is the first to be served. The most recent is the one that gets served first. This provides a depth first search, DFS. Again, if we're starting at A, we will have a frontier that looks like this. A, and rather this is a stack now. So how can I draw this? That works. I draw it like this, so going sideways and going upwards. We explore A. Next version of the frontier will have B, D, E, presuming that we explored them in alphabetical order, just by chance, non-determinism and all that. We'll explore E, because that's at the top of the stack. That's how this works. E will provide us with F and G. So we have B, D, G, no, FG. B, D, F, G. G gives us nothing, so now we just have F, D, B. F can expand into C and K, so we have B, D, C, K. Exploring. Have we got it? Yeah, we have done it. So exploring K gives us nothing because we've already been to that. Now it's just C, D, B. C gives us nothing, so D, B. And B, and then empty. So we draw out what these paths took. This one first went to this one, this one. No, pardon me. It went to E first, so it went from this one to this one. Then it went to F, then to K, then to C. Then it went over to... Oh, whoops. D will reveal H. H will be explored. And then leaving B. Pardon me. Okay, we go to C. Then we'll go over to D, which will expand to C, which will then expand over to B. And we've been everywhere. That is the most unclear thing ever, but you can see it while I'm drawing it, so, works. Alternatively, breadth first search will go from A to B, to D, to E. Then we will go to F, to H, to K, to G, and then over. That's not. Oh. Okay, I'll just rub out. There. It'll go from G over to C. So two different paths they take based on if you're doing breadth first or depth first. Not going into the most detail into this because we've done it on 3 separate occasions now, I think. But still, something to be aware of. Looking at the lecture notes, there is nothing more than that. Okay, so yeah, so that's all it is. That's all for today. This was a bit of a long one. Thank you for watching.